Okay, so we've got quite a mix. So most of you are kind of somewhere in the middle, but we've also got people who are slightly less confident and slightly more confident. Okay. So let's run through the learning objectives. Firstly, we're going to be looking at the electromagnetic wave spectrum, and we'll be knowing that light that we see all around us every day is part of that electromagnetic wave spectrum. We're going to look at the other waves aside from light. So we're going to look at radio waves, microwaves, infrared, visible light, which is the light that we obviously see around us day to day, UV radiation or ultraviolet radiation, X-rays, and finally gamma rays. So these are all different types of waves that are part of the electromagnetic wave spectrum. We'll be understanding that the speed of light in a vacuum is 300 million meters per second. And we will learn a bit more about visible light and how it's made up of lots of different frequencies of light waves. And finally, we will know that different frequencies of light have different colors. We'll learn about the terms transparent, translucent, and opaque. You might have come across those words before. And we'll also cover that light always travels in straight lines. And we'll know how to represent that by using a ray diagram. Okay, so electromagnetic waves. Waves can be split into two groups depending on what they're actually traveling through. So you've got mechanical waves. Examples of these would be water waves, seismic waves. So seismic waves are waves that travel through the Earth's, the depths of the Earth. And sound waves are also types of mechanical waves. Okay, so these sorts of waves, these mechanical waves, have to travel through a substance. And they transfer kinetic energy. So kinetic just refers to movement. So mechanical waves travel through a substance and they always transfer kinetic energy, so some sort of movement. So water waves are traveling through the substance water. Seismic waves, deep in the Earth's crust, are traveling through the Earth. Sound waves are traveling through air. On the other hand, what we're going to be focusing on today are electromagnetic waves. Okay, so these waves don't need to travel through a substance, but they can. So just remember, mechanical waves always travel through a substance. Electromagnetic waves don't need to travel through a substance. Okay, they can travel through space, which is a vacuum. Okay, a vacuum is just kind of a volume, but without any matter in it. Electromagnetic waves transfer electromagnetic energy. Okay, so just like mechanical waves are carrying kinetic energy, electromagnetic waves are always going to be transferring what we call electromagnetic energy. And there's lots of different examples that we'll look at of types of electromagnetic waves or EM waves. But the examples in this slide are light waves, radio waves, X-rays, and microwaves. Okay. So visible light, it's a certain range of frequencies within the electromagnetic spectrum. Okay, so light is an electromagnetic wave, the light that we see all around us day to day. This is a type of electromagnetic wave, and it's called visible light because we can see it with the human eye. Okay, some of these other electromagnetic waves we can't see with the human eye. Visible light is one that we can. And electromagnetic waves are transverse waves. Okay, so this is when the vibrations of the waves are at 90 degrees in which the travel and the direction of the wave is traveling in. Okay, so electromagnetic waves, as we said, they don't need a substance to travel through, but they often do. So that means if they don't need a substance to travel through in order to transmit from one place to another, they can travel through space because space is a vacuum, okay? So just to reiterate, transverse waves are where you've got the wave and it's got oscillations or vibrations, and these are vibrating at 90 degrees relative to the direction of energy transfer, the direction in which the wave is traveling. Okay, so I'll just repeat that because that's a really important point. Transverse waves are where you've got the oscillations of the wave or the vibrations of the wave traveling at 90 degrees to the direction of energy transfer. The other type of wave, which is, I guess, a little bit less relevant to today, but we'll just cover the two definitions anyway. Longitudinal waves. This is where the direction of oscillations or vibrations is at parallel to the direction of energy transfer. Okay, so the vibrations of the wave are parallel to the direction in which the wave is traveling. But we're mainly going to be focusing on transverse waves today because electromagnetic waves are transverse waves. So these are the types of electromagnetic waves. Okay, remember I said that it's a spectrum of waves, and you can see there's different wavelengths. So if we're looking from the left-hand side, we're starting off with radio waves. These are the waves, the electromagnetic waves with the longest wavelength out of all of them. So you can see here, the wavelength is a lot longer. That's one wave, compared to the right-hand side where the wavelength is really, really short, okay? So radio waves, all of these things we make use of as humans. Okay, so radio waves are used in communication, for example, TV signals, but also because their wavelength is so long, it can be, you know, thousands of kilometers in length. We use them for communication that stretches all the way out to space with satellites and that sort of thing. So radio waves are the electromagnetic waves with the longest wavelength. Okay. Then we move on to microwaves. As you know, obviously, we use microwaves in cooking. So what happens is the microwaves are being absorbed by the water molecules in your food when you're heating it up. And that absorption of energy causes the particles in your food to vibrate, and then it gets heat is kind of released, and that's how your food gets hot. Microwaves are always also used in communication as well. So when we're, you know, talking on the phone, for example, that does involve microwaves too. So microwaves have a slightly shorter wavelength than radio waves. Okay, so as we go from left to right, the wavelength is going to get progressively shorter. The next wave that we can think about is called infrared or IR. Okay, and infrared is also used for communication. We can't see infrared as humans, but some animals might be able to. In terms of where we might find infrared, it's all over the place, but things like heaters will emit infrared. Okay, so just to be clear, infrared radiational waves have a shorter wavelength than microwaves and an even shorter wavelength than radio waves. If we're thinking about visible light has a shorter wavelength than infrared, and visible light, as I said earlier, is the light that's visible to the human eye. Okay, it's what we can see all around us. It's why we can see objects in front of us. And it's a spectrum of color that we can see. And as I'll talk about in a bit, red has the longest wavelength and violet has the shortest. But again, we'll look at that on another slide. Next is UV light or ultraviolet light. You guys might have heard of this. This is emitted from the sun and it causes us sunburn. So when we've been out in the sun for too long, there's all that radiation coming from the sun, and these UV waves or ultraviolet waves are what causes sunburn or damage to our skin. Then next on the list, X-rays. Some of you might have even had an X-ray. So we use X-rays to view bones in the human body. For example, if someone's had an accident where they've fallen over and you might think that a bone is broken, you go to the hospital and have an X-ray, because the X-ray allows you to image that bone and see whether there's any break anywhere. And finally, gamma rays. So these are the waves in the electromagnetic spectrum, and they've got the shortest wavelength. Okay, you can see here. So this would be like one wave. If you just follow my cursor, you can see how short that wavelength is compared to the wavelength of a radio wave, which is far greater. Okay, gamma rays. So this is obviously really short wavelength. It's actually used to kill cancer cells because it can damage our cells if we're exposed to it. But we also use gamma rays to sterilize medical equipment. So what I mean by that is, if you were a patient going to a hospital and you're being treated for something, and the nurses and the doctors are using equipment to treat you, you want it to be sterile, don't you? You don't want there to be any nasty bugs on there. These gamma rays, really high radiation, can kill those nasty bacteria so that you don't get an infection. So it's just going to be a bit of a repeat of what I said, but let's go through it anyway. So radio waves have the longest wavelengths in the electromagnetic spectrum. They can often be thousands of miles or thousands of kilometers. And here it says the wavelength can even be longer than our planet. Okay, so super, super long. They can travel really great distances, and that's why we use them for communication. Microwaves have the second largest wavelength, so they're also used in communication. For example, when we're talking on our mobile phones with each other, that all relies on microwaves because they're really large, so they can again cross from really long distances from one side of the planet to another. Infrared wavelengths, they're slightly longer wavelength than visible light, but we can't see infrared. Okay, it's invisible. Our eyes can't pick up that wavelength, but we can feel it. So if you have like an electric heater, for example, that heater will emit infrared waves, and you'll feel it as heat or warmth on your skin. Some animals, not humans, but other animals can actually see infrared, so things like bed bugs, mosquitoes. Visible light, it's called visible light because we can see it with our own eyes. Okay, and this is the spectrum that I was talking about. So we've got this spectrum of, electromagnetic waves running from radio waves all the way through to gamma rays. But within visible light, a part of that spectrum, we've then got this other spectrum, okay? So this is the color red. So visible light is split into all these different types of color that we can see: red, orange, yellow, green, blue, indigo, and violet. And depending on their wavelength, that corresponds to, what color they'll be. So red is around about 700 nanometers. NM is just nanometers. And they get smaller as you move from red to violet. Okay, so red has the longest wavelength, and then orange has a slightly smaller wavelength. Yellow light will have an even smaller wavelength, and so on from green to blue to indigo to violet. Okay, so just to reiterate, red has a wavelength of around 700 nanometers. Violet has a smaller wavelength of about 400 nanometers. And this is the light that we can see, hence why it's called visible light. So ultraviolet radiation, or UV, is shorter than violet light, and we cannot see it. Okay, so we only see visible light. We can't see ultraviolet radiation. Some insects, however, might be able to see ultraviolet radiation, so things like bees. And if you've been out in the sun for too long, it's a really hot day, when you get sunburn on your skin, that's being caused by UV radiation damage. So you're getting a lot of ultraviolet light being emitted from the sun onto your skin. You're absorbing that UV radiation, and that's why you get sunburn. As we said, X-rays have a very short wavelength, and we use X-rays in hospitals to look at the bones of the body if someone is suspected to have some sort of break. And finally, gamma radiation. Okay, so this is the shortest wavelength in the electromagnetic wave spectrum, and it's used in radiotherapy. Radiotherapy is a type of treatment for cancer. So because these have a really short wavelength, they can actually kill your cancer cells, which is why it's great as a treatment, because you want to get rid of that cancer tumor. And like I said earlier, gamma rays can also sterilize medical equipment. So sterilization just means that you're cleaning a machine, for example, or some sort of equipment, and you're making sure that it doesn't have any, bacteria or viruses on the surface of it. And that's to stop people getting infections when they go into hospital and they're operated on, for example. Okay, and this is just again to show really long wavelengths of, say, radio waves and microwaves, whereas you've got a really short wavelength for things like X-rays and gamma rays. Okay, so light. Light that comes from the sun and lamps that we use in our houses is known as white light. And white light is basically just a mixture of all these frequencies, visible light, so that it appears white to our eyes, but it's actually like this whole spectrum. Okay, so light waves come in many different frequencies, just like those electromagnetic waves that we just spoke about, and we group them into 7 different colors. Okay, so red, orange, yellow, green, blue, indigo, and violet. And we can see, just to remember, red has a wavelength of about 700 nanometers. Visible light, UV radiation has a wavelength of about 400 nanometers. Okay, so red light has the largest wavelength and the smallest frequency. Okay, you can kind of think of it like this: if red has like a really large wavelength, frequency is just how many waves pass a point in 1 second. Well, if the wave is, really, really wide and it's got a large wavelength, you're going to have less actual numbers of waves passing through a point in, say, 1 second, because they're just so big. Violet light has the smallest wavelength and the highest frequency. And you can think of it like this. If violet has a really kind of narrow wavelength that's really small, you're going to have more narrow waves passing through a point in 1 second, because they're much smaller and narrower. Okay. Okay. So these are obviously, the colors of the rainbow as well: red, orange, yellow, green, blue, indigo, and violet. So we can remember the order using this mnemonic. Richard of York gave battle in vain, because the first letter of each of those words corresponds to the color. So R for Richard, R for red, O for off, O for orange, yellow for York, yellow, light, G for gave, G for green, and so on. Okay, so Richard of York gave battle in vain. This is always the order of colour that visible light presents, and you wouldn't have, say, red next to green, for example. Okay, it always goes in the order of red, orange, yellow, green, blue, and indigo and violet. Okay, so time for another Slido. Which colour of light has the largest wavelength? Green, indigo, or yellow? So I'll just give you a few moments to answer. Okay. Really good, guys. Just wait for a few more responses because they're still coming in. It's great to see lots of you interacting. Really good. Okay, so fantastic. Well done. Exactly. So out of those three, yellow is going to have the largest wavelength. Okay, so we've said that white light is emitted from the sun or, lights in our house, and it's a mixture of all these different types of light. Okay, so they've all got different frequencies: red, orange, yellow, green, blue, indigo, and violet. All of these make up what we call white light. If we want to see white light being split up into these different coloured lights, we can use a glass prism. So it's kind of like a glass pyramid, but in 3D. Okay, raindrops can also split the sun's light, making what we see as a rainbow. I'm sure you guys have seen rainbows whenever it's sunny, but also raining at the same time. That rain will split up the sun's light into all of these different constituent colours. Okay, so we can see here when the white light is traveling, it hits a glass prism or a raindrop. It travels through the glass prism, and then it gets split up into the rainbow colours, and that's what we can actually see with our eyes. Okay, so light waves can travel through any transparent or translucent material. Okay, transparent means that you can see through an object. If an object is transparent, you can see right through it, no problem. So things like a window, which is made out of glass, or air, or even clear water. Okay, so you can see through a transparent object. A translucent object means light can pass through, but not completely. So you do get some light going through, but it's not completely as clear as it would be with something like looking out of a glass window. Okay, so examples of translucent objects might be frosted windows. So, windows that have like some color on them. They might be slightly darker, for example, than like a normal window. Sunglasses, because the shades of the sunglasses are dark, but you still get light passing through those sunglasses because obviously you can see out of them when you wear them. And something like vegetable oil as well. Okay. An opaque object, it means that you can't get any light that goes through it. Okay, so if I don't know, you had a massive brick in front of you, you had it in front of your face, you wouldn't be able to see what's directly behind that brick, okay, because it's opaque, no light can get through it. So yeah, they're solids. Okay, another Slido. I'll give you a few moments to answer this. So a window is something because light can travel through it. Is it transparent? Is it translucent? Or is it opaque? Really great to see all of the interaction, guys. You're doing really well. Give it a few more moments to see if anyone else wants to answer. A few more moments. Still got people answering and joining. Okay, so let's have a look. So well done, guys. Most of you got the correct answer. So a window is, yeah, a window is transparent because light can travel directly through it. So when you're looking out the window, for example, it's made of glass. You can see directly through that glass very clearly, and that means that light is traveling through it really well. Okay. So light can be detected with what we call photosensitive materials. What that means is, so the word photo in physics or in science just refers to light, okay? So any sort of process, for example, something like photosynthesis you might have heard of, photo refers to light. So that process is going to be dependent on light somewhat. So we can see light, obviously, with our human eye, which is shown actually on this image here on the left-hand side. This is an eye. And we can also detect light using a camera. Okay, when we take pictures, that all depends on the ability for the camera to detect light waves. So if we think about how our eyes detect light, how do we see? Our eyes basically focus light. Light is emitted from an object in front of us. For example, you know, you might actually be looking at some sort of light or an apple or something. The light is emitted from the object. It's a wave, so it travels into our eyes and it hits the photosensitive material in our eyes called the retina. Okay, let me just get my cursor. So this is the word retina. It's kind of at the back of the eye. Okay, so this is the front. This is where your iris and pupil is. This is the iris. This is the pupil. Pupil's the black part of your eye. You've got this object in front of you. The light is going to be emitted from the apple. It's going to pass as a wave. That light wave is going to pass through your eye. It's going to hit your retina, which is the photosensitive cell part in your eye. And then the retina is going to produce electrical signals when it detects light. Those electrical signals then get transmitted to your brain along your optic nerve. So the light hits the retina detects the light, produces an electric signal that then travels through the optic nerve up to your brain, and then your brain processes that as an image, and then you see the apple. Okay, but all of this obviously happens super quickly because, as we'll find out later, light travels really, really quickly. So that's how eyes detect light. How does a camera do it? It's kind of similar. So you've got your object in front of the camera, obviously. So this is our object, the yellow circle. It could be anything. That light wave is then transmitting. It's going through the lens of the camera. And then you've got some sort of photosensitive material in the camera that detects light. Again, it produces electrical signals, and then that ends up producing an image here. And then we can view that image. okay, on a screen. So for example, on the screen of the camera or on the screen of your phone, which obviously has the camera in it. And then that information can be sent to a printer, for example, and you can print out that image and you've got your photo. Okay, so let's think about the speed of light. It's a really important number in physics. Remember I said that a vacuum is basically just, a volume of space that doesn't have any matter in it. The speed of light, nothing else travels faster than light. Okay, it's the fastest thing in the universe. And scientists have measured it at approximately 300 million meters per second. Okay, so when light travels in a vacuum, it's traveling at around 300 million meters per second. Okay, so it's really, really fast when you think about it. You almost can't even imagine it. And just of note, all the other electromagnetic waves, they all travel at the same speed as well. So all those waves that we spoke about, radio waves, microwaves, for example, all of those also travel at this speed of 300 million meters per second. Okay. Light travels as transverse electromagnetic waves in straight lines, okay? So it's not going to kind of be a wavy line that when light's being transmitted, it's always going to be traveling in a completely straight line. That's why when we use diagrams to show light traveling, we're always going to be using a ruler to show that light travels in straight lines. Okay, so we've got a light bulb here. Although when you turn a light bulb on and it starts emitting light, it looks like the light is just kind of all over the place, going in all different directions, but it's actually just straight lines going in each direction, okay? So it's not going to kind of be random and wavy and curly. You're always just going to get straight lines of light being transmitted out of the bulb, okay, in different directions. That's what's actually happening when you turn on your light in your bedroom, for example. Okay, so we always draw light waves as straight lines using a ruler. And then we've got a little arrow showing the direction of the light. Okay, so it shows the direction of energy transfer. So you can see here, this is our light bulb. This is our light source, obviously. We switch it on. The light is going to be traveling in a completely straight line into our eyes. And you've got an arrow here to show the direction of energy. So it's going from left to right in this example. This is what we call a ray diagram. So in physics, we use ray diagrams to show the direction of light. You can think of it like, you're illustrating a ray of light using this straight line and arrow. And the ray diagrams, they just show the direction that light's traveling in. Okay, it's not showing the direction of vibrations. We know that the vibrations in a light wave, well, it's a transverse wave. So the vibrations or oscillations are going to be at 90 degrees to the direction in which the wave is traveling in. Okay, so we use ray diagrams in physics when we're, studying light. It's useful to show how light travels between different substances and different mediums, and what happens when light then hits a new object of another material. Okay, so ray diagrams. Just to repeat that, so ray diagrams are really useful for showing how light travels from one object to another or one space to another. And they also show what happens to the light when it hits another different material of a different density. So when light meets a new surface, it can be reflected, it can be absorbed, or it can travel through, okay? It can be refracted, and we'll have a look at that in a moment. So when light meets a new surface, it can do three things. It can be reflected, so it might bounce back off the surface. It could be absorbed by the object. So all objects tend to absorb at least a bit of light. The light's shone onto the object, it will then absorb some of that light wave. Or the light can be refracted. Okay, so it can travel through the object. Most of the time, light, when it hits an object, it will be absorbed and also reflected at the same time, so simultaneously. Okay, so let's do another Slido. Which sentence is false? I'll give you a few moments to answer that. So which sentence is false? Light waves travel at 3, and then you've got a lot of zeros here, so you've got to work out, remember what speed we spoke about? What speed does light wave travel at, and how many zeros are in that? Light waves travel in straight lines. Is that true or is that false? Light waves are longitudinal waves. Is that true or false? Light waves are part of the electromagnetic spectrum. So which of these, or which sentence is not true? Which sentence is false? I'll give you a few moments to think about that. We're getting different responses. Give you a little bit more time to think about things. Okay, so which of these sentences is false? Light waves travel at what speed in a vacuum? Light waves travel in straight lines. Light waves are longitudinal waves. And finally, light waves are part of the electromagnetic spectrum. Okay, so we've got a mixture. Okay, let's have a look. So the correct answer is light waves are longitudinal waves. Okay, so this is false. We know that light waves are a type of electromagnetic wave, and therefore, because all electromagnetic waves are transverse waves, light has to be a transverse wave. Okay, so that's where, just to repeat, the definition of a transverse wave, the oscillations of the wave, the vibrations of the wave are at 90 degrees relative to the direction in which the wave is traveling. So if the light is traveling in one direction, the vibrations of that wave are going to be 90 degrees relative to that direction. Okay, the other statements are true. We know that light waves travel at 300 million meters per second. So that's the number of zeros there. My cursor's gone. We know that light waves travel in straight lines. Okay, they're never kind of curly or wavy lines. It's always straight lines. And we know that obviously light waves are part of the electromagnetic spectrum. Okay. Okay, so let's summarize and then we'll have a short break. So we know that light is part of the visible light part of the electromagnetic wave spectrum. It's called visible light because we can see it with our own eyes. We know that the electromagnetic spectrum is made up of all of these different types of waves. So the really big radio waves and microwaves, infrared that we get from our heaters, for example, obviously visible light that we see, UV radiation or ultraviolet radiation, and then the really kind of narrow high frequency X-rays and gamma rays. We know that in a vacuum, the speed of light is faster than anything else in the universe, and it's estimated to be around 300 million meters per second. We know that visible light is made up of many different frequencies of light waves. Okay, so remember that visible light has different colors and different frequencies. We know that the different frequencies of light have different colors. We know how to define what a transparent object is, so that's where light completely goes through it. We know that a translucent object is where light partially passes through that object. So something like frosted glass, for example, or dark sunglasses where the lens of the sunglasses are, brown or black. And an opaque object, such as, a solid apple, is opaque because light cannot get through it at all. We now know that light travels in straight lines. Okay, and we represent that using a straight line drawn with a ruler, and then we draw an arrow on that line to show the direction that light is traveling in from one object to another. Okay. So I think we will have a 10-minute break now. So we'll be back at 54 past. That's okay. Okay. Hi guys, I hope you can all hear me. So let's start where we left off. Okay, so right. Okay, so we just did a summary, okay? Okay, so we've got a practice question. We've got a ray of light traveling from the spotlight here at the top. Okay, so we've got an actor on stage. This is the actor, they're on stage. We've got the audience, and we've got a massive light at the top of the room shining onto the actor. So which line shows the ray of light? Okay, so it's either line A, line B, or line C. Again, I'll give you a few moments so that everyone can have a go and think about which one it might be. Just try and think, what did we say about how light travels? Give you a few more moments. People might not be back from the break yet. Really good that people are interacting. I'll give it a few more moments because I think we had more people answering before the break. Okay. So these are your results. And the correct answer, you did really well. So it's going to be B, isn't it? Because if we go back, we know that light travels in a straight line, okay, and that was line B. Okay, so you can see here that line A is curved, isn't it? It's not traveling in a straight line, so it can't be A. Similarly, line C is also curved, so we know that it can't be C either. B represents the light traveling in a directly straight line from the spotlight onto the actor. Okay, light always travels in a straight line, and we show the direction of light using these arrows. So it's going from the spotlight to the actor. Okay, so let's have a think about this one. How long does the light take to travel from the spotlight to the actor? So if you want to put your answers in the Microsoft Teams chat, and there should be a moderator who can publish your answers and let you know if you're getting the answers right. How long does light take to travel from the spotlight to the actor? Is it about 100 millionth of a second, about a tenth of a second? Does it take a second, or does it take 10 seconds? So have a think. I can't actually see the Teams chat, but I'm sure you guys are all putting your answers in there. I'll just give you a few moments to do that. Okay, so how long does light take to travel from the spotlight to the actor? Does it take about 100 millionth of a second, about a tenth of a second, about a second, or about 10 seconds? And remember, what did we learn about the speed of light? How quickly does light travel? Okay, so the correct answer is the top one, The light probably takes about 100 millionth of a second, and that's because we know that light travels so incredibly fast. It travels faster than anything else in the universe that we're aware of. Okay, so light in a vacuum travels at 300 million meters per second. Okay, let's do some more questions. So part B, so the actor's voice sounds different to the people in the front and back rows of the audience. How does the actor's voice sound different to a person in the back row? Okay, so you've got the actor on a stage, you've got lots of different rows in the audience. How does the actor's voice sound different to a person in the back row? I want you to put your answers in the chat, and the moderator will be publishing those and helping you guys out. So just give you a few moments to think about that. Okay, and finally, the second question. So complete the sentence with the words longer, shorter, or exactly the same. When the actor is at the back of the stage, the time his voice takes to reach the audience is, and you need to select one of those words, so longer, shorter, or exactly the same. Okay, so let's go through these questions. So the first one, how does the actor's voice sound different to a person sitting in the back row? Well, it would be quieter, wouldn't it? Imagine you're in a hall. I'm sure you guys have done school plays, for example. If you're sitting right at the back, you're not going to hear the actor's voice as loudly as someone who's sitting right in the front row. Okay. And then similarly with the second question, when the actor is at the back of the stage, the time his voice takes to reach the audience would be longer. Okay, it's going to take more time because the distance between the audience and the actor has now got larger if the actor's at the back of the stage. Okay. So any questions, just pop them in the chat. Again, sorry, I don't actually have access to the Microsoft Teams, but I'm sure there are some lovely moderators there who can answer any questions that you guys may have. And please feel free to ask questions as we go on. Okay, so now we're going to look at some new learning objectives. We've kind of covered the electromagnetic spectrum. We've covered light as well. So we're going to be firstly understanding what the law of reflection is. Remember I said that when light hits an object, it can either be reflected by the object, it can be absorbed by the object, or it can even pass through the object, what we call refraction. Okay, so firstly we need to understand the physics law of reflection, because that's really important when we're thinking about how light travels between different objects. We're going to define what an incident ray is, what a reflected ray is, what a normal line is, what an angle of reflection is, what an angle of incidence is. We're going to learn about the terms refraction, absorption, scattering, image, and object. So there's lots of terms. They might seem a bit confusing at first, but we'll go through them really slowly. We'll repeat them a few times to make sure that it's really going into our heads. And then we'll be doing some questions to test the understanding. We know what ray diagrams are. So ray diagrams show the direction of light using straight lines and an arrow on it. So we'll be drawing ray diagrams to show how virtual images are seen in mirrors. We'll be using ray diagrams to show refraction and reflection. And again, we'll be going over those terms in a little bit more detail. we'll be understanding how lenses work, okay, and then we'll be drawing diagrams of those too. Another learning objective is that we'll be understanding how cameras take photos, and we'll also be understanding a little bit of what might seem like biology, so a bit about how the eye works, and what the different parts of the eye are, including the retina, which we've kind of already spoken about, what the cone cells are, what the iris is, what the lens is, and the pupil. You might have heard of these words before. They're all just different parts of our eyes. And we're going to be knowing that white light can be split into that rainbow spectrum using a prism. And finally, the last learning objective is that we're going to learn about how coloured objects reflect and absorb.